Welcome back. We're doing Thermodynamics 1 homework. Homework number 4, problem number 3. Homework number 4 is on first law analysis of a closed system. So piston cylinders, rigid tanks, that kind of thing. And so number 3 is the just trying to read it right. 2.21b out of Koretsky. Okay, so 2.21b out of Koretsky. Okay, so it provides a picture. So let's just draw the picture they have. So they have a piston cylinder. They say atmospheric pressure is equal to 1 bar. They have a mass here that's really specific. So mass is equal to 20 megagrams. I mean, we could be, there's some pretty specific numbers here, so we're just going to round things, okay? The area is equal to 0.5 meters squared. The mass in here is equal to 0.2 kilograms. The height is also something very specific. It's 0.7172 meters. We're just going to say the height, HT, is equal to 0.7 meters. Okay. Again, for simplicity. There's also a spring attached to this. And the spring has a force equation equal to minus kx. And K is equal to 1.7 approximately newtons per meter. Okay, so that's the spring constant. Which is a lot of nonsense. Okay, so initially the spring exerts no force on the very thin piston. What does it mean by very thin piston? It means it's massless. Okay, so really all the mass is coming from that mass that I put on top of it. So I put the mass on top, causing the gas to compress until the force again balances. During the compression process, I have specific amount of work that is done. So work is equal to this very specific amount, which is basically 620 kilojoules per kilogram of work. Okay. Okay. Now it says precisely draw the process on a PV diagram, draw the area that represents the work. I'm not, we could do that, that's part A, but we're really just doing part B. How much heat is transferred during the process? Joules per kilogram. Okay. So I just want to do an energy balance on this thing. Okay. I draw my boundary, draw my thing, okay. Gotta have my assumptions. Okay, assume no shaft work. I don't see anything spinning. So no shaft work. Is it? Well, obviously it's not adiabatic because I'm actually trying to find what Q is. Okay. Is it? It's going to be constant pressure because I'm going to have a pressure, here, and that's going to be constant throughout. Does it say anything about whether it's a steam or a gas or anything? Okay, it does say it's pure water. Okay. So I do have water in here. Okay. But yeah, this is, this is going to have a certain, now, it doesn't have a pressure like at this condition, but it is going to have a pressure at the end condition. Okay, and so, but I might not need to know if it's constant pressure or not because I have a work term. So let's not assume it's constant pressure. It might be, it might not be, but let's for now be on the safe side. Now we do know that delta KE and delta PE are about 0. Okay, and we do know it's a closed system. So we do know those things, so everything else we can kind of glean from that, okay? And just move forward with those as our assumptions right now. So first we need our mass balance, sum of m dot I. Oh, we need I already assumed a closed system. N minus summation of m dot E exit equals dm dt control volume. This obviously is 0, this is obviously is 0. So dm dt, this control volume is equal to 0, which means that m2 is going to equal to m1 through the same kind of steps, but let's be explicit about them. So dm is equal to 0 once we integrate, once we bring time over, and then we integrate, and then we bring them together, and then we're just going to say that that's my mass. Okay, so mass is constant. Now we do our energy balance. Okay, m dot I hi plus 1/2 b squiggly squared I plus g z I minus summation of m dot E exit n he plus 1/2 b squiggly squared E plus g z E plus q dot plus work dot equals du dt plus ek plus ep control volume. Okay, so that goes to 0, that goes to 0. Changing kinetic energy and potential energy is about 0. There's nothing coming in, there's nothing coming out. There is work, there is heat. Okay. And so when I'm all said and done, okay, I need to know my temperature, right? No, am I trying to find my heat, or am I trying to find my temperature? Let's see here. It says how much heat is transferred during the process. Okay, so does it say anything about it being constant pressure? No, it doesn't. Okay. All right, but this, we have two work terms. We have boundary work, we also have the work of the spring. Okay. Oh. Okay, so we have q dot plus work of the spring dot plus work of boundary dot equals du dt of the control volume. Okay, I don't care about time. Okay, and so we're going to call this boundary work. I think is it the total amount of work, or does it say the total amount of work? Okay, it says during the compression process, this amount of work is done on the system. Okay, and so it actually that's not the boundary work, that is the total work. Okay, so this is combined. Okay, but we're going to get rid of the time term, so we have Q equals work plus mdu, because my mass is constant. I can pull that, simplify it into that step. Okay, and again, assume that's pretty constant, so to speak, or I mean pretty, regular. So this is going to equal work plus m times u2 minus u1. Okay, specific. All right, let's look at this. Well, I know what I start with, and then I know what, okay. So what I don't know, in a sense, is what's the pressure when I'm all said and done, or rather, what's the volume, okay? And so what I would need to do at this point in time, is I would need to do a pretty complex force balance to figure out, okay, what's my final height? Okay, so you've got that mass, that's gonna, so you've got the force of the mass, which is gonna be, gravity times the mass of the mass times, let's see here, mass times acceleration. Yeah. So that's going to be the force of that, and then you're going to have the force of the spring, which again is minus kx, okay, And so they're going to balance, and then you also got the force of atmospheric pressure, which is basically the external pressure times the area. Those are all going to balance. So basically, you've got Fs going upwards. You got mass going downwards. You got pressure going downwards. So minus Kx should equal P external atmosphere plus G times m. You'd have to solve to get your delta, to get your new x. Okay, and with your new x, okay, this is going to tell you your new total volume, how much mass, and this will give you your specific volume. Okay. Which now you have, okay, well, you don't, let's see here. Do you know the final pressure? Okay. Yeah, you would know the final pressure because it would be these, this kind of, you'd have this total force divided by area. So you have this kind of, net force that you'd have to account for. You could back calculate what the pressure would be. So now you have a pressure. Now you have a specific volume. Bring that together and you can get your temperatures and your internal energies. You have your work, and then you can get your heat transfer. Okay. So that's really more of a kind of complex force balance problem. A little goofy, but it's not a bad problem. But it's really all about what's the energy balance when all's said and done, and it really just kind of simplifies down to that. So, and that's what I really care about in these kinds of